Good afternoon, everyone. Today, I will introduce NosWalker, a decoupled architecture for out-of-core random walk processing. So, what is random walk? There are some walkers in a graph. Each walker starts from a given vertex. In each step, it first randomly samples an edge from the current vertex. Then, the walker is moved to the destination of the sampled edge. By repeating these two steps, the walker can reach his termination condition. Random walk serves as a foundation for many applications, such as deep walk and node-to-walk for node embedding, personalized PageRank, random walk denomination for graph mining, and so on. Take the node embedding applications as an example. Random walk is used to extract a large number of random sequences from the graph. These sequences are fed to the downstream learning task to compute gradients and update models. In a large graph, there can be billions of walkers. In recent years, there has been a significant increase in the amount of data. This leads to the explosion of graph size. The graph size exceeds the memory capacity of a single machine. It's expensive to build a distributed cluster that can hold all the data in memory. As a result, many systems have been proposed to make it practical and economical to analyze large graphs on a single machine. According to our investigation, these systems can be viewed as following a block-centric design. They carefully organize the graph data on disk. In each epoch, they load a block of edge data in a small set of sequential disk reads, and they access only the data in the current block to update vertex data. The reason for this design is that the execution and I/O patterns of most traditional graph analysis applications can be reduced into GSPMV algorithms. Based on the general out-of-core graph processing framework GraphQi, Zhang Mob is the first out-of-core random walk system. In each epoch, it loads a subgraph from disk and moves all workers residing in this subgraph one step forward. GraphWalker, which is also built on GraphQi, is the current state-of-the-art out-of-core random walk system. To improve the I/O efficiency, it loads the blocks with the maximum workers, and it introduces asynchronous worker updating and adopts the re-entry method. Thus, worker can be moved as much as possible until it goes out of the current block. Nevertheless, according to our investigation, the optimizations made by these two systems are still not enough. We measure the average edges read per step metric for the two systems. As we can see from the left figure, the two systems require much more edge to be loaded than NosWalker. As the right figure shows, it leads to the significant performance gap. We found a unique property of random walk. The sampling process is related to only edge data. Thus, sampling process can be decoupled from the processing of walkers. As the figure depicts, the future sampling results are listed in the box. Instead of sampling only once, we preemptively complete the sampling that will occur in the future, and reserve the surplus sampled edges in memory. The pre-sampled results can be viewed as a succinct representation of the original edge data. Now, we give an example process to show how the pre-sampling technique can help with performance improvement. We load a vertex and sample more than one edges. One of the edges are used to move worker 2 from V0 to V2. The others are reserved in memory. Similarly, worker 0 is moved to V0. Since they are pre-sampled edges for V0, worker 0 can be moved to V3. In this way, even if the vertex is not loaded, workers can be moved by using the pre-sampled edges. This process is illustrated by the animation. An outstanding example is the second step of worker 1. After moving it to V0, we successively move it for 3 steps without the need to load any edge data. There is a long tail problem when GraphWalker moves workers asynchronously. The last 30% execution time is used to process the last 3% of workers. Even though GraphWalker tries to load the current hottest block, as depicted in the figure, the proportion of data accessed in each I/O is still not high. It exacerbates the long tail problem. Modern SSD can achieve both high throughput and high LPS, but not simultaneously. Our benchmark shows that for Intel SSD P4618, the sequential read can achieve up to about 3.1 GB per second, and the LPS can be up to more than 600,000 LPS. To address the long tail problem, we propose the adaptive block granularity technique. When the active workers become sparse, only a fraction of the data in a large block is needed. NosWalker switches to fine-grained block mode. We take the figure as an example. Since they are workers locating at V1, V4, and V6, the corresponding fine-grained block is marked by the bitmap. NosWalker loads only the marked fine-grained block. Another limitation is the cost of loading and saving worker states can be also very large. On the one hand, Zhang mob manages all the worker states in memory. It results in the limited scalability. On the other hand, GraphWalker uses small fixed-length worker buffers to manage worker states, and it swaps worker states between memory and disk. It contributes up to more than 60% of the total disk I/O. Although the number of workers can be very large, these workers are independent of each other. We can generate workers dynamically. As the figure depicts, we only need to keep a part of workers in memory and never spill them out to disk. These workers never store due to swapping their states between memory and disk. We simply generate new workers after older workers terminate. This mechanism reduces the cost of loading and writing worker data directly to 0. The realization of the architecture change is also not straightforward. Some implementation challenges need to be solved. We introduce other optimizations to further resolve the long tail problem and reduce the possibility of stalling due to pre-samples run out. More details are introduced in the paper. Now, we start to present the results of our experiments. Here is our test bed. The datasets we use are listed in the table. We use the basic random walk to study the performance of NosWalker. In the experiments with a different number of workers, when the number of workers is less than 1 billion, the main bottleneck is graph loading. NosWalker can use pre-sampled edges to keep walkers moving and adaptively shrink the block size to significantly reduce I/O. In the experiments with different walk lengths, when the graph is larger than the memory, the execution time of all these systems increases almost linearly with the walk length. But NosWalker is always 30 to 95 times faster than GraphWalker. In these experiments, NosWalker achieves up to 2 orders of magnitude speed up. We conduct experiments to measure the effectiveness of our main optimizations. Generating walker dynamically works well when the number of walkers are large. Adaptive block granularity makes a difference since it addresses the long tail problem. Pre-sampling edges reduce a lot of disk I/O, especially when they are weights on the edges, such as the dataset K30W. The I/O reduction breakdown analysis cross-validates the source of the performance gain from these optimizations. We compare with the in-memory random walk systems, standard RW and MingXing. NosWalker still has advantages over these systems when we take into account the time of graph loading. In conclusion, based on the decoupled architecture, we implement 3 main optimizations: pre-sampling edges, generating walkers dynamically, and adaptive block granularity. And finally, NosWalker achieves up to 2 orders of magnitude speed ups. Thank you for your attention.